Buongiorno a tutti.
Good afternoon. My name is Elisa Martelli, and I'm about to introduce to you to the main contribution, which is going to be performed by my former colleague Maurizio Giuliano, who is now professor at Verona University. Specifically, we'll talk about the consumption of SO2, of a reduction, sorry, of SO2 in the bottle. And first of all, I would like to introduce to you my company, which is called Vinventions. It was set up in 2015, and the intent was that of becoming the most innovative and reliable company worldwide, capable of supplying complete solutions for the closing of and stopping of both still and sparkling wines. It has 7 brands. And the last two presented, or the latest two presented, are service brands in that we have wine quality solutions, which will be further mentioned later on, and wine marketing solutions, which proposes marketing services. As for the other 5 brands we propose, we have different types of stoppers in enology, and the best well-known is possibly Nomacorc. It is famous due to the plant cork technology and co-extruded cork production, then Syntex for synthetic stoppers, when we have Ollinger for natural cork stoppers. And soon will be also on the market with microagglomerated corks, which are made in such a way that there is no glue, and then screw caps with the Vintop name brand, and then recently we got a distribution almost worldwide of Vinoloc with the glass stopper. Now, let's focus on today's core matter, and I would like to tell you about wine quality solutions, which derives from a cooperation that lasted more than 10 years between the research department of the company and 14 academic partners from all over the world. The goal being that of making it possible for enologists to have real-time solutions in the winery by means of using a number of services that we offer. We have a series of analyzers, and you saw them on the slide, and I will now list them. The first child, so to say, is Nomasense. You might know this already, and it analyzes oxygen. It works based on a luminescence system, so that a light is emitted by the system. Then there is a sensor which is attached to supports that are put in bottles and bagging box, and it has to be in a clear medium. Of course, the sensor reacts, and based on the concentration of oxygen that is in the medium it is put in, and the instrument measures that. It is particularly interesting as a tool because you can separately measure not only dissolved oxygen but also gaseous oxygen, and we will go back to that. The second analyzer that we have in our range is called Nomasense CO2, which measures CO2 in still wine. The technology is based on spectrophotometry, non-dispersive infrared spectrometry, and it measures accurately the value of CO2 in wine in a range from 50 to 2.50 milligrams to 2.5 grams. We then have a color analyzer, which is called Nomacolor. This is really a portable device. It looks like a joystick, and it is something that works based on the principle of reflectance, which means that you do not need to prepare the sample. We have the sensor in master wine in a half a centimeter optical cuvette. It expresses color by means of copolar and Descartes coordinates based on the CLab model. You can measure the color directly or comparing it with the reference standards that the enologists decide to use. It is very easy to use. The last one I would like to mention is called Polyscan, and it measures the polyphenolic component in must and wine. It is based on an already existing technology. It was used in the past already. And it is linear voltammetry. The positive aspect of this is that an analysis is made with no need for preparing the sample, and you use single-use electrodes whereby you can dispose them afterwards, and you do not need to do any calibration nor any cleaning. You have a number of indexes, and you selectively detect the oxidation of the various substances. Oxidation means a release of electrons, and this is what the tool records. Then you have an electrochemical curve that is a sort of fingerprint of the sample, and this gives us a number of indexes. This is again the overall picture of what we make and offer. Oxygen control is what I would like to talk about now in order to introduce the reduction of SO2. Here you have the pickup, that is the increase in oxygen in the various vinification and aging processes. That is during the entire life of the wine, from the moment when grapes enter the winery to the tasting of the wine. And you have an initial phase of fermentation where, irrespective of the type of grape, the quantity of oxygen is substantial. And you know very well that must can also consume rapidly the oxygen in the process. So we have a macro-oxygenation period in this initial phase. And this happens over a time period of a few hours only. After fermentation this fermentation is completed, you have aging in the winery, and depending on the type of wine making, red or white, you have a different approach. So during the fining period in the winery, you have this micro-oxygenation, and during the entire process, you have maximum a number of additional milligrams per liter per month. After bottling and after aging in the bottle, as a consequence, the quantities of oxygen are even less. And here we talk about nano-oxygenation, irrespective of the specific permeability that we will talk about later on when talking about the stoppers and corks. So you have a few milliliters per year. So this is the process of oxygenation of the wine. In addition to that, we also need to consider a variable which is always there if you want to bottle wine, and which always has a negative effect on the sensorial features of wine, which is the bottling. If enologists were able to do so, they would totally avoid that moment, because the wine has been prepared with the right SO2 level for bottling, and oxygen is, though, always harmful to the wine, and it changes the profile of the wine. If we actually consider what oxygen is, and I mean the oxygen that gets into the bottle, we have basically two sources of oxygen which come from the bottle. We have the oxygen which is in the wine, and which several wineries, I would say all wineries can measure in terms of a parameter. And then we have another parameter, which is the head space oxygen, which is the quantity which is in between the stopper and the upper level of the wine. And this has a major impact on the quality of the wine. And then we also have the permeability of the cork or stopper. So it is oxygen which comes into the wine through this closure, because we have, first of all, the oxygen transfer rate of the cork, which is how much oxygen enters into the wine per year. And the other parameter to be considered is the outgassing, which is the quantity of oxygen which enters the bottle in the moment when the cork is pressed by the machine. Each cork, as you know, is a sort of sponge. When you press it, to be put into the bottle, then after in the following days, it grows again in a way and it releases oxygen in the bottle. What about the quantities? As you see here from the graph, there is a huge fluctuation. We did hundreds of tests and analyses all over the world. What you see here is the dissolved bottled oxygen in gray, and the head state oxygen is in red. You see immediately at first sight that gaseous oxygen makes out approximately 60% of the total. Not only that, if you consider uncertainty bars for the head state, you see that they are fairly high and much higher than those pertaining to dissolved oxygen, DO. This means that the head state is the main source of variability from bottle to bottle. The total oxygen deriving from bottling is how much. Here you have a number of 18 actually tests performed in California, and we have good values here. 1.5 milligrams liter per oxygen in total due to bottling. Many people here are European, and we know that the European value is 3 milligrams per liter, which means basically double as much. There is no difference in the ratio between DO and HS oxygen, nor the uncertainty and variability from bottle to bottle. The dissolved oxygen possibly is the smaller component out of the total, but this does not mean that we shouldn't monitor this parameter and also take it into account. Here you have the evolution of dissolved oxygen during the normal bottling process, from the filling to the end of the process. And you can compare and contrast numbers with the previous table. And you see that at the beginning of the bottling process, you have an increase in the DO, not the total one, but just the dissolved oxygen, exceeding, or rather reaching, the average of the measured and monitored bottlings in the cellar. And then that stabilizes and increases again at the end of the process of bottling. The reason is that initially and also at the end of the process, unless you work very accurately, you run the risk of mixing things and inserting into the bottle, putting into the bottle a huge quantity of oxygen. So I think that the strength of NomaSense is that you measure gases also during the process, and not only in the bottle. You measure the tank, for instance. You can use probes and sensors to that end, and you know whether you are working correctly or not. Now, I would like to offer you some figures with reference to both closures and bottling. The stoppers and corks have variations, as I told you. If we consider a range of good permeability that should not lead to a defect, we talk about a range from 0.5 to 3 milligrams of oxygen in a year. Our selected a rather tight closure we have, let 1 milligrams of oxygen go through per year. If we consider that the average is TPO is 3 milligrams per liter, this basically corresponds to 3 years of shelf life. Which means that really you have to measure the bottling oxygen in order to be able to control its quantity. Now, what does the enologist do? It prepares the wine for bottling, and he does so by adding the right quantity of SO2 too, in order to protect it. Actually, it is not so that this always produces the effect you want. Here I have an example of a French wine that was prepared for bottling with a high dose of SO2, 50 milligrams per liter. It is a white wine. Basically, a number of bottlings were simulated by means of adding a certain quantity of total oxygen. So we have one control, and there we added 0.5 milligrams per liter. Then we have an additional 3 milligrams per liter, which is a first step, and that is the European average. And then we have a second group up to 5 milligrams. And this is a wrong bottling. This represents a wrong bottling, which, as a matter of fact, is something that we find in real life after rather often. Because you can have vacuum pumps that do not work as they should, and you can reach these values easily. So you protect the wine. It is closed with these 3 levels of total oxygen. And then after 4 weeks, we asked a panel of experts to taste the wines and to describe them. And here we have the corresponding graph. You see that after 4 weeks from bottling, both the thesis with 3 milligrams of oxygen per liter, and especially the one with 5, had really a number of oxidation and oxidative characteristics, which means TPO always has an effect on the quality of wine, and it is always a negative one. One of the things that we wanted to understand better was the evolution of the wine, starting with from the oxygen that entered the process. And it is especially closure producers that were interested in that, as we are, of course. And we could not only consider dissolved oxygen to make that assessment. We performed the test, and we measured the quantity of oxygen entering the bottles. Here we had 4 closed units with different permeability corks, and we calculated the total consumed oxygen. That is all the oxygen which enters the bottle and which is consumed by the wine. This comes from the summation of the dissolved oxygen, the head state oxygen, and the ingress oxygen, permeability of the cork, and outgassing. At the same time, we also did tests on wines closed, and made the analysis of free SO2, which meant analyzing the reduction in free SO2, irrespective of the entry oxygen. What we obtained there, we have on the x-axis or on the y-axis as free SO2 and TCO on the x-axis. You have a good correlation here between the 2 parameters, and you do not find this correlation if you only consider dissolved oxygen. What we considered or judged to be sort of interesting, which led to additional studies, was the coefficient of correlation, which is 2.5. In literature and in enology in general, we consider a ratio between oxygen and milligrams of free SO2, which is 1 to 4. While in this case, and not only in this case, but also later on, we detected that basically the ratio is smaller, and this is also possible. It is 2.5.
Now, before I leave the floor to Maurizio, I would just like to give you some takeaway messages. I'd like to reiterate that oxygen in the bottle is not just the dissolved oxygen, but it is a summation of several parameters. Of course, the dissolved oxygen has the lion's share, but there's also the head space, the cylinder of air between the cork and the surface of the wine, and obviously the oxygen that percolates through the closure. The head space actually accounts for 60% of the total, and so you need to measure it. Now, decreasing the bottling oxygen by just 1 milligram makes it possible to extend the shelf life of a wine by approximately 1 year, and this is important when you assess the shelf life of any wine. The loss of SO2 is connected not to just dissolved oxygen, but to the total oxygen consumption, and this ratio appears not to be 1 to 4.